Hi everyone. So yes, my name's Susie Roy. I work for WSP. New to wearing glasses, so I might be putting these up my head and down again to see my slides. So the presentation I'm going to give here is a project that we've done with Southern Water, but also with the BGS. So working with Lou Morris and Andy Farrant as well. Yeah, it was all about looking at surface karst features within the chalk catchments that Southern Water operate or own the abstractions to understand more about the risk to water quality. So why does Southern Water need to know about holes in the ground? The main driver for this was a catchment risk assessment process. So understanding that risk to water quality. Southern Water have got around 91 groundwater abstractions, the majority of them from the chalk, and over 95% of them from the catchment risk assessment process are identified as being at risk from either pathogen detection, so bacterial pollution, or from nitrate or pesticides. And we'd identified through doing that catchment risk assessment process, looking at the data, that the pathogen detection was, pretty much driven by rainfall and the antecedent conditions. There's also low-level detection of permitted pesticides, so things like glyphosate, metaldehyde as well at the time. This is a few years ago now, which suggested that there's a fast flow path to the water table because there were pesticides being detected that you would expect to break down. But I'd reiterate that that was at low levels rather than above the drinking water standard. And so in this slide, there's a little image there from, I think it's from the UK Groundwater Forum webpage, I think, or a NERC study, which just sets out, in terms of pathogen species diameter, and in terms of the pore spaces and different aquifer materials, just shows that increased risk when you start to talk about fissures and solutional features as opposed to just the chalk pore spaces in terms of transport of things like cryptosporidium oocysts, for example. And just generally, the project followed on from a pilot study that Southern Water had already undertaken. So Richard Gamble at Southern Water, and supported by Stantec as well, to look at karst features in the Brighton and Worthing area, so the chalk of the South Downs around there. So our project scope was to roll that approach out to a much wider area, so an area probably more than 1,000 kilometres squared, looking at the chalk catchments that Southern Water have in the north and the east Kent chalk, and then also across in Hampshire, so North Hampshire, and then on the Isle of Wight as well. And our scope of work was to look at literature review to understand what the differences were, or if there were indeed differences in terms of how surface solutional features develop in these two different areas, so in Kent and Hampshire and the Isle of Wight, and then to understand what the implications were for water quality risk. We were going to then do a desk-based mapping to identify surface depressions, which could potentially represent solution features, and then refine that, and then check that information or that desk-based approach in the field by doing a field campaign. Then that was followed by refinement of the mapping, and finally, in going through this presentation, I kind of felt, gosh, it was a bit of a sledgehammer to crack a nut kind of problem, but it was thinking about how has that data set then been used by Southern Water to kind of help direct what they do in terms of catchment management and in terms of groundwater protection. So I'm really glad that Lou and other people have talked about that aspect of things already today. So I'm going to recap just on chalk karst development, and also very glad that other people have talked about this already. The focus, I suppose, of this discussion or my presentation is really around those surface karst features, so dough lines, sinkholes, well, stream sinks, sorry, that form from acidic runoff from the head deposits, so the clay with flints, the Paleogene as well, in the 2 different areas or 3 different areas we're talking about, and that are developing through that either collapse of those features into the chalk, so those strata into the chalk, or from runoff at the edges of those features. So it's really focusing on that kind of feature as opposed to the deep karst that people have been talking about here, so the conduits. So I think we've probably seen this figure a couple of times already this morning. So stealing it from, well, it's referred there. It's something that Lou and Andy put together. So what we took from our literature review of what happens in the Hampshire and Isle of Wight chalk, in terms of the Hampshire chalk, it's this kind of conceptualization of a cross-section from north to south of the chalk dipping down underneath Paleogene strata and getting much more of these solution features developing at in the runoff areas, but also having these deeper conduits that lead to the development of the Bedhampton and Hammond Springs, so the really big spring features. But also, so thinking about moving further to the west, so Bedhampton, Hammond Springs is obviously the Portsmouth Waters area, but, you know, looking at Southern Waters Otterbourne abstraction, where they've got a tracer test from the Pole Lane stream sink, where they have a travel time of less than a day from about 700 metres away. So, you know, there's clearly development of karst within the Southern Water area as well. When it came to the Isle of Wight chalk, however, because the strata there dip quite steeply, there's less of an outcrop area, and also the overlying Paleogene sediment's quite a bit thicker, so there's less scope or less area for development of karst features, although there are karst features there, including dissolution pipes, sorry. So it does exist, but probably not as evident in the Isle of Wight chalk. So thinking about the northeast and north and east Kent chalk, in that area, it was, so sorry, I should have said just in the Hampshire chalk area, the chalk's quite deformed in terms of folding, so anticline and syncline development, trending sort of east-west across the outcrop of the chalk, whereas in north and east Kent, the kind of controls on hydrogeology are more around the faulting and joint structures, and you have this dipping strata from the sort of south, with the scarp slope of the chalk in the south towards the north, and quite a more of a significant thickness of clay with flints deposits in that area compared with the Hampshire area. But then you have these tight, narrow, steep-sided valleys where you get solutional features developing. You still have the same karst development as we found from our lit review around stream sinks and large dissolution features and cave. I think cave features have been identified at depth as well. But then because the Paleogene in that area is quite different to the Paleogene in the Hampshire area, where that's more like the London clay and Reading beds, you've got the thanate sands, which are quite permeable. So you do have that the occurrence of recharge through those strata into the chalk, which leads to sinkhole dissolution features and collapse features there. So moving on to somewhere where I'm a bit more comfortable, because it's a bit simpler probably for me. So in terms of the approach we took for trying to understand where these surface depressions were, so the candidate karst features, surface karst features we were trying to find, we took LiDAR data, so the Environment Agency's LiDAR data, which is available at a 1 to 2 metre resolution. In this figure, you can see it here, the red areas are gaps in that data set. So we had to purchase some additional LiDAR data from Blue Skies, and that came at a 50 centimetre resolution. And then we had to use the 5 metre DTM data for areas in Hampshire where we had a gap. So in some areas we had higher resolution data, in other areas we had not so good resolution data. But we put all that information together at our catchment scale. And what we did, so this is the figure that I've done, it's quite noddy. Basically, the process in GIS was to take the LiDAR information, use the fill tool in GIS to fill in the surface depressions, and then take the original LiDAR surface from that. So you end up with a data set that's just the fill impressions. And then you can use that to create polygons, which give you the sort of extent in 2 dimensions of the depression, and then also the depth as well. So that was the process in GIS. It's all automated. We set ourselves a limiting boundary for the geometry of the karst features, because we were coming, you'd obviously come up with millions of features across the area we were looking at. So we set ourselves a limiting geometry of 1 to 50 metres wide, and then half a metre to 4 metres deep. And that's based on the literature that we'd looked at. 5 minutes left. Right, I'll crack on. So then we needed to undertake some sense checking of that data set, because obviously there's a lot of artificial or anthropogenic features in it. So we automated a process where we used GIS OS mapping of roads and rail cuttings or railways to understand where there might be anthropogenic features. We looked at the BGS Britpits data to understand where there were chalk pits or historic chalk pits. We wanted to keep those into our survey. And then just using the East Kent area as an example, we screened out man-made features where we'd identified them with a buffer in GIS. We also screened out urban areas as areas that we wouldn't be looking at, and we screened out active pits. And that top middle figure shows where we'd identified features that lay within a 100-metre buffer of the thickness of the drift cover or superficial cover being 10 metres thick based on the BGS superficial thickness data set, and also within that boundary of the Paleogene or clay flints head deposits. So we ended up with a more refined data set where we'd kept every point in, but we'd allocated whether we could identify it potentially as a karst feature or anthropogenic or unknown. And we also then compared that to the BGS's, or the BGS helped us by comparing it to their data set, their databases of karst features and their memoirs, and the speleological, or the records of the Chelsea Speleological Club as well. So we ended up with a data set that was ready for us to take out into the field and do some checking, sense checking of. We could see that we didn't have that good a match to the BGS's karst data set, and perhaps that was because of some inaccuracies in the location information that comes with the older records. But some of these features might have been infilled because because chalk pits get reworked or filled in by the landowners. And there may have been some, well, I already said there was issues with the lower resolution of the DTM data in Hampshire as well. But so our next step was then to do the field mapping. So we had a really enjoyable 4 days of mapping with Andy Farrant in the field in Kent, around Rochester, and then in Hampshire around Winchester, where we refreshed our science brains, I suppose, when it came to geology, but also understanding the different types of vegetation that you can look at to understand what the soil type is, whether it's alkaline or acid. So looking at things like sweet chestnut and looking at clematis as well. But then also thinking about chalk pits and how they were built, or how they were developed by the farming community in, sort of the 1600s, 1700s, and what shape they would be, what the morphology of them would be compared to a doline feature. And it was a really interesting 4 days. And after that, we felt we were well prepared to go out into the field. So we developed our mapping approach, which was to only go and look at sites that were accessible by public rights of way. We weren't going to look at active quarries. We did have a flyer that we developed in case any people were interested. So we did this mapping post lockdown. I think we were just about let out, so it was in 2021. So we had these flyers for people because we thought there might be lots of people out walking on the public rights of way. And we collected data using an art collector database that was already set up with the underlying information from the field mapping. And the process that our mappers, undertook was to, if they found the feature in the field, great, record or check the morphology and the size of it, understand if there was chalk in the base of it, so there's bare chalk in the base, was there water in the bottom of it, was there pollution in infill, and to take a photograph of the feature. If they couldn't find it, we wanted to understand why we couldn't find it, or was it because it was covered in vegetation because we were mapping in the summer, so obviously there were crops in the field. Was it because it was on private land, in which case could Southern Water ask for further access from the landowners? So then once we completed our mapping, we then went to refine that data set back in the office. So this is again looking at East Kent and just looking at a summary of what we found. So from 900 odd features that we went and looked at in the field, we could only find 44% of them. So it's not great, but that's some of them. And of that 44%, the majority were man-made, which you'd expect. But then 10% we thought were karstic, basically from our field work. So then going on to the project outputs, and this is where I come back to me thinking, well, we were making a lot of effort. So how were the outputs quite useful? And that is in that table there for the total. We looked at about 6,000 sites, but actually only about 6% ended up being identified as karstic features. The outputs were maps for Southern Water to use as part of their catchment risk assessment, with each of the features identified as either chalk pit, a doe line feature, or unclear, or a stream sink. And then these photographs, and I realised how hard it is to take a photograph of a karstic feature or landscape and then be able to see what you can clearly see with your own eyes. But yeah, so having looked at the people's photographs today, I'm not quite sure the quality of these, but we did have photographs also of fly tipping when that's within chalk pits as well. So there's lots of information there in terms of pollution risks. In terms of how the outputs have been used, so the maps have been used as part of the catchment risk assessment process. So that report that has to be done by Southern Water, by all the water companies, to understand the different risks, so in terms of the sources and pathways for their areas, their catchments, and to understand that risk of that shortcut in terms of the pathway to the saturated zones, so into the water table. And just an example here is one of this catchment where we're looking at pesticide risk mapping to understand. So at the bottom, you've got the Bentazone risk map that's used by the voluntary initiative that's based on groundwater vulnerability. So it's interesting that Lou was mentioning that this morning, because the groundwater vulnerability mapping does include information about Karst, but I'm not sure what the resolution is. Whereas this mapping we've got here is a much more low, or it's much more focused in on the catchment itself. So very useful to kind of refine that understanding. And then I can see I've got less time to do this, but the really interesting thing for me, and these are a couple of examples of sites that we went to see when we were out with Andy on the training bit of the project, was looking at a stream sink. So for example, this is a dairy farm where they were practicing mob grazing. So that's where they move cattle around, but quite intensively on bits of land, and they move them around quite rapidly, but you end up with land that's quite covered in cowpats. And there was a field where you can see here in the figure, you've got a subsurface flow feature, a conduit that had got collapses in one part of the field. So that's the picture of it there behind some barbed wire. But you can see from the mud that water comes up through it. And so the risk there is that, that's draining that field direct to a water feature that's next to the farm. So there's evidence of just that kind of, if you had that understanding as a farmer or catchment officer, what advice would you give in terms of better practice? I would say less cows on the land myself. And then this was for me, quite interesting in terms of thinking about wet weather surveys as well. So it was a farm where the Google Earth image shows you've got some lagoons, which we couldn't see on the day we went out, but they're close to the farmyard. Presume they use them for, I don't know, runoff or something like that from the farmyard, or washing water. But then below, or to the right of that, you've got a valley that's kind of like I think it was a slope that goes down to the chalk pit on the end, on the right-hand side here. And there were 3 stream sink features within that area, but there was also a slope. So you can see the silage bales being stored with some bits of old metal, and then that came to a slope downhill, which the bottom of that, there was a little stream running, which then came to this muddy stream sink area. And then there was a hole that I made my colleague put a stick into, and it was a deep hole. There wasn't any water in it, but you could see there was mud. So it's evident that runoff was going to that location. And in the past, that silage clumpy area had been used for manure heap, I think, from Google Earth historic photos. That's it. I'm sure I've gone over. So thank you very much to you for all listening. Thanks to Southern Water, so Richard Gamble, who isn't here, I don't think, and Will and Chris, and then thanks to our GS people, Sarah Butler and John Collini, who slaved over screens to develop all of those figures. Thanks to our mapping team. Thanks to Andy and Lou very much for all the advice and the review time. And then finally to Ben Fretwell, he was retired since then, but he was our technical reviewer. So that's it. If you have any questions.